Hey guys, Kanoa here. So I've been reading a lot of Facebook posts about people having a lot of distrust for the media and a lot of unknown going around about the coronavirus and the vaccines. And so I wanted to produce some content talking about just what the current landscape is as far as what a vaccine is, how it reacts to the body, and what we should be expecting moving forward as far as timelines and the different advances in vaccine technology. Now, I know it's a very controversial topic, and so I want to address this early on just by saying that there's no known correlation between vaccines and autism. Now, I know it's a very heavily debated topic, and so for those who are new to it, I would check out Andrew Wakefield. He was the original physician who came up with the study saying that the MMR vaccine and autism were correlated. Now, his data has never been able to be reproduced, and he's had his medical license revoked by the medical community or the scientific community. So we're all going to make our own decisions, whether it's choosing to vaccinate or not vaccinate. My overall goal with this video is just to provide a basic understanding of what a vaccine is, so that when we have discussions about this, we're all a little bit more educated as far as how they work and what the current status of the technology is. So just a brief overview of where we've come from. So Han China was where variolation was first practiced. Now, variolation was just a term coined for providing immunity against smallpox. Now, they would take the people who are infected with the smallpox, take their scabs and rub them into the wounds of healthy people in order to provide immunity. So from here, our understanding of vaccines has drastically improved in the 18th century England when Edward Jenner decided to inoculate people with cowpox in order to provide immunity for smallpox. Now, the smallpox vaccines they attempted were too virulent, but they had seen that milkmaids actually had immunity to smallpox. So from here, we proceeded to what are now practiced in smaller communities as pox parties. Now, a pox party will never be recommended by any health professional because what they basically are a gathering of people in a room and they incubate together with the virus. Now, people believe that they have more control and that it's a more natural process of vaccination. However, this can be extremely dangerous since the strength of the virus from person to person is unknown, as well as the amount of contact people are exposed to. People still practice this today, but it is not recommended. And as we've seen with COVID-19, it's extremely dangerous. Now for our modern vaccines, the basis of our technology has been centered around either the live attenuated virus or a dead/killed virus for maybe the last century. The live viruses have been weakened in a laboratory through multiple mutations in order to make them safer for the public. But for those who are immunocompromised, the killed virus allows them to come in contact with the virus and build immunity. However, the immune response is generally less and requires more frequent dosing. But this has been the basis of our technology for the past century. So now let's talk a little bit more about the current state of the technology. So to my left, I have the graphic that I shared on my personal Instagram, and for me, it was very exciting because I got to see all the different preclinical, clinical candidates for vaccines that are in the works. Now, for those who aren't really familiar with vaccine technology, we're going to break down as far as how each of these work so that you have a better idea for what to expect from them. So in order to understand how vaccine works, we must first understand how the coronavirus works. So the coronavirus works by having spiky proteins that act as like a lock and key sort of mechanism where they come in contact with the cell wall, open it up, and then they're allowed in. From there, the virus is able to infect the DNA and change it to alter the way they make proteins so that they make proteins the way that the coronavirus wants them to. In addition to hijacking the cells into making more protein, the virus will actually use the cells to replicate itself and spread throughout the human body. If we're able to create the protein that allows the coronavirus to enter the cells and basically tell our cells to recognize the tertiary protein structure and label them as being bad, then we can provide immunity to our body. So we see when looking at this graphic, you see live attenuated, dead, DNA, RNA, viral, even protein treatments that can be used as far as a vaccine. And so let's start breaking down how each piece of technology works. So looking at this overview of how each vaccine can be used, feel free to pause here, since this is a lot of information. This is just a generalized landscape of all the different vaccine candidates that we have, and it's not that complicated. The overall goal is just to produce the protein that's seen on the coronavirus. However, the biggest takeaways are, 1, we don't know how strong of an immune response we actually need for immunity, and 2, we must validate that some of these vaccine systems actually work, since some of them are the first of their kind. So we see from the infographic that in the bottom right corner, the overall goal of a vaccine is to trigger an immune response, which would be producing the antibodies that will bind to the surface proteins on the actual virus. So here's also where things get interesting. You look towards the top of the graphic, you see that viral treatments are a viable option for vaccine candidates. Now, it seems a little counterintuitive using a virus to fight a virus. However, when you think about the coronavirus, it's a very efficient system. It enters the cells, delivers whatever gene it wants to, and then infects your body. Now, what if we could program viruses to do the same exact thing to fight off the coronavirus? And so that's the idea. And we've seen with lentiviral treatments where you basically insert a gene of interest into the lentivirus, it infects your body, and it delivers whatever genetic information to produce the proteins that your body needs. It hasn't been widely approved yet by FDA. However, one big drawback to viral treatments is that you must choose a viral vector that's not going to be toxic to the human body. And the second major drawback is the manufacturability. We're not currently at the point yet to where we could put a viral-based vaccine in the hands of enough people quickly enough. With more advances in viral manufacturing, it'll bring the cost of viral-based vaccines down. However, we're just not there yet. All right, so look at the middle part of the graphic. We see that DNA and RNA are viable treatments for vaccine candidates. Now, we can't just inject free-floating DNA or RNA into our bodies because we have free-floating enzymes called either DNase or RNase that will go around searching for free-floating genetic information and chop them up and render them useless. So we have to insert them into some sort of carrying vesicle that will protect them, allow them to enter cells before they're released. Now, companies like Moderna are hyping up their liposome technology, and all a liposome is if you want to think of it as like a fat bubble. And so you inject your RNA treatment into their fat molecule, inject this into the human body, and what the fat molecule is able to do is bypass the cell membrane of cells, and then dissolve, exposing it to the RNA, and then the RNA will change the way that the cells make protein and start making therapeutic antibodies. Now, when considering the manufacturability of the liposome, it is dramatically easier to create many different liposome-based vaccines as opposed to making different viral ones, protein ones, because every time you change any part of a protein, you're changing the actual functionality of it, and every single manufacturing process from protein to protein, antibody to antibody, and virus to virus is different. As opposed to with the liposomes, all you're basically doing is injecting genetic information into some sort of fatty water molecule and then just changing the genetic information you put in there in order to serve different purposes. When thinking about the scalability of DNA or RNA-based vaccines, the sound of it sounds monumental, that it's one manufacturing process, and all you need to do is just know which RNA treatment you need, and you kind of just plug it in wherever you need, and you could treating a wide variety of different genetic disorders. And so going back to that infographic, when I see that DNA and RNA-based treatments are in the pipeline, it's very exciting for me as a scientist and investor because it's going to unlock a whole new level of medicine that just previously was not accessible. And so drugs will be significantly less. And I think this is going to make healthcare more accessible to developing countries, and we're going to have new cures to illnesses that we didn't have before. Now, as far as like the process with clinical trials, since this is the first of its kind, usually a new drug, you have to file a new drug application, and it's a more lengthy process to get approved by FDA because not only do you have to prove that this works, but you have to prove that this treatment's not going to be harmful to the body, and the whole manufacturing process has to be validated. So there's a lot of checks that need to be fulfilled in order to make this actually implemented. However, due to the coronavirus, this timeline is sped up quite a bit. So I'm very optimistic and I'm very hopeful, but as far as vaccine candidate goes, we're not supposed to expect anything until next year. So like always, wash your hands, stay safe, cover your mouth whenever you go out in public. However, if you found this video very helpful, please share it with your friends. Please like and subscribe to the channel. Hopefully you guys learned something from this. All right, thank you.